Alright guys, welcome to lesson 9.3. Now this is most likely going to be the most critical lesson in this section because this is where we start talking about Taylor series. And Taylor series are a pretty big deal, okay? It's kind of what this chapter is entirely based on, alright? Okay, so let's go ahead and read through this for a minute. In this section you'll be finding polynomial functions. So these expansions are like polynomials that can be used to approximate transcendental functions. Alright, so let's talk about what that means. You guys know polynomials are like x to the fourth, x to the third, x squared. Those things are polynomials, okay? Transcendental functions are like e to the x, ln of x, sine x, cosine x. Those are the main ones we're going to work with. So those are polynomials and transcendental. So we write a transcendental function as a polynomial function, and then we're able to do certain kinds of math on it that we cannot do otherwise. Okay? Alright, so p of x is a polynomial function used to approximate some other function f. They must contain the same point with the same x value c. P of c equals f of c. You might be like, what is this talking about? They should have the same slope at that point. So their derivatives at the first part of c should be equal to each other, their derivatives at the second, and so on. Okay, putting this all together gives us a Taylor polynomial expansion. If f of x has derivatives, it can be approximated by this. Alright, check this out, guys. This is nuts. So we start with f of c. Alright, c is the point where we're going to center around. At the beginning, we're always going to do 0, and then we're going to expand out and do some other numbers. Then we go f prime of c, x minus c. Then we go f double prime of c over 2 factorial x minus c squared. F triple prime of c over 3 factorial x minus 3 to the x minus c to the third, and on until we go to the nth derivative over n factorial x minus c to the n. Now, this pattern works because, even though you can't see it right here, this is x minus c to the 0 over 0 factorial. This is x minus c to the 1 over 1 factorial, and then 2 factorial like that. Okay? So we just don't write that stuff because they go on to 0. Alright? Now, at the beginning, what this is talking about right here, these are called nth degree Taylor polynomials. When we center them at 0, they have a special name. They are called the Maclaurin polynomial. I think that's how you say it, centered at C. Okay? When it's not centered at C, it's called a Taylor polynomial. Right? If it's a different number, that's just the more broad term for it. Okay? And so you can kind of see that it's the same thing, just at 0. So all my x minus c just become to x. X minus c squared becomes to x squared. X minus c to the third becomes x to the third. Because c is 0. Okay? So it makes it a little more simple. So we're going to start off with it at 0 so that you guys can kind of make sense of this. Alright. Use the formula for the Maclaurin polynomial to find the 5th degree Maclaurin polynomial for e to the x. Now, a 5th degree polynomial means an x to the 5th. Okay? Okay, so here we go. First of all, we have to take a bunch of derivatives of e to the x. Now, guess why we're starting with e to the x? Because it's so great, guys, because every derivative of e to the x is e to the x. That's why we're starting with this one. Now let's plug in 0. So e to the 0 is 1. The first derivative, e to the 0 is 1. The second derivative is 1. And so on. These all equal 1. Okay? So now we're going to write it out down here. Alright. So it starts with f of 0. So that's 1. And then it goes f prime of 0 over 1 factorial x to the first. Okay? Now, we don't need that 1 over 1 factorial. It just makes it look a little bit messy. So I'm going to do that. Okay? And then it's the second derivative. That's 1 over 2 factorial x squared. And then we do the third derivative over 3 factorial x to the third. the fourth derivative over 4 factorial x to the fourth, and then the fifth derivative over 5 factorial x. Okay? That is, notice like right here where it says P5, it's actually 6 terms, but it's a 5th degree polynomial. Okay? And this is a very good approximation for e to the x, right? When we extend it into infinity, it is e to the x. So the actual like formula here, x third over 3 factorial, x fourth over 4 factorial, and then xn over n factorial, and then it keeps going forever. That is exactly e to the x. Now, we were talking about this a little bit in class, okay? And so I have this here. I had it extended out. Let's look at this. So like 1. I forget I have to put y equals, right? And then remember when we go plus x, it's like a little bit closer. Plus x squared over 2 factorial plus x to the third over 3 factorial, which is 6, plus x to the fourth over, over 4 factorial, which is 4. Okay, and this polynomial is centered at 0. So like right here at 0, right, these two things are very, very close to each other. All right, these two graphs are very, very close to each other. The more we zoom out, the less like approximate they are. Now, if I were able to type that into infinity, these graphs would look exactly the same. Okay? So, you can extend the general form to like an infinite series. So, again, it says like right here, provided f has all derivatives, meaning you can keep going with the derivative, it never stops. We just extend these out to infinity. The Taylor series is different because it's about x equals c, meaning not at 0, and then the Maclaurin series is at 0, and we extend them out forever. So we have power series, which means functions with like exponents, for functions, even if they can't be a geometric. Like e to the x was geometrics, but we have some things that are not. Okay, so check it out. Fourth order, so fourth order means I need to go to x to the fourth. Taylor polynomial, f of x is cosine, c is pi. Okay? So let's start with cosine, and let's take some derivatives. The derivative of cosine is negative sine, and then the derivative sine is cosine, the negative just stays on it. Then the derivative of cosine is negative sine, so that goes back to positive sine, and the derivative of sine is cosine. And like these will keep on going forever and ever and ever, Okay, now we're going to evaluate each one of them at pi. Alright, just so you guys remember our unit circle, right? And pi is like over here. And it's a point negative 1, 0. And what we're going to remember is cosine is the x coordinate, sine is the y coordinate. Okay? Alright, so let's fill these out. Cosine of pi is negative 1. The negative sine of pi is 0. Negative cosine is negative 1, so that's 1. Sine is 0. And then cosine of pi is negative 1. Okay? So here's my my polynomial. Alright, now remember, it starts at just regular f of x, which is negative 1 in this case. Okay? And then the next one is 0 over, the next one is 0 over 1 factorial x minus pi to the 1. And then it's 0 over 2 factorial x minus pi to the 2. Sorry, this is not 0. I'm like going too fast. Okay, the numbers on top of the factorials that I'm going to like place in here are coming like directly off of here. Okay, I'm just going a little fast. Alright, so that's negative 1, and then the next one is 0, and then the next one is 1, right? And then the next one is 0, And then the next one is negative 1. And that's my fourth order Taylor polynomial. Okay? So we used all my numbers up there. Which, you guys, means that, you know, every other term is like becoming 0. So let's see if we can figure out the pattern. So now, not just going to 4, but like extending out to infinity, okay? Negative 1, and then it's going to be x minus pi squared over 2 factorial, and then it's going to be minus x minus pi to the 4th over 4 factorial, plus, and then it's going to be x minus pi to the 6th over 6 factorial, minus, okay, and it's going to go along like that. Alright? There we go. Okay, so the next question says, use your Taylor polynomial from example 2 to approximate cosine of 3, and we're just going to do the polynomial, the 4 terms, right? Not infinite terms. So for the 4 terms, so cosine of 3 would be negative 1, and then 3 minus pi squared over 2 factorial, and then 3 minus pi to the 4th over 4 factorial, and then this alternated, right? So that's minus plus minus. Okay, and if I'm doing the example, the one from like example 2, that means I'm going out to only the 4th term to approximate this. Okay, now I'm going to go ahead and put this into my calculator. Let me pull up my calculator here. Okay, so let's go ahead and type this in. Negative 1 plus, whoops, I need negative 1, not minus 1. Okay, negative 1 plus, and then it was 3 minus pi to the 2 over 2 factorial, which I know is 2. Okay, I'm going to type in the factorial because it's just 2 times 1. And then it's minus 3 minus pi to the 4th over 4 factorial. Now, if you want to type in the button, it's under math, probability, factorial. Okay? And here's what I get. Negative 0.98999. So, let me say that is equal to negative 0.9899925. I'm just going to put a bunch of zeros, okay? You guys can see that. Now, what's interesting is, let's see actually what cosine of 3 is, okay? Now, I need to be in radians, which I am. Okay, good. Cosine of 3. Now, this is like the exact value. That's crazy. Negative 0.989999249. This one was like 250. Alright, you guys, that means that a 4th order Taylor polynomial actually approximated that to the 10, 100,000, 10,000, 100,000, million, 10 millionth digit, maybe? Millionth digit or 10 millionth? Like, 3 terms. Literally 3 terms, and it approximated it out to just the 7th digit was different. But, like, if we round, it would have been out to the 8th digit. Okay? 3 terms. That was very, very accurate. Now, why was it so close? Part of the reason why it was so close was we centered it at pi. And pi is approximately 3.14. And I'm using cosine of 3. And so the number I'm plugging in is very, very close to the center. Okay? Let's say instead of 3, we tried something like 6. It's not even very close to it at all, right? So let's say instead of 3, I'm just going to use this right here. And let's say we try to approximate the cosine of 6. Okay? And you guys know 6 is not very closely centered at pi. So now when I say, okay, what's the cosine of 6? That is, not only is that not a good approximation, that is a terrible approximation. That is not even close. And it's because 6 is too far away, right? So, okay, so let's move on to this next one here, right? Okay, Maclaurin series for sine. Here we go. All right, let me start with, this is sine, and we need to do all my derivatives, okay? Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of sine is cosine. So that goes to negative cosine. Derivative of cosine is negative sine, so that goes back to positive sine. Derivative of sine is cosine. Okay? Now, because it asked me to use, to find specifically the Maclaurin series, we're evaluating all of these at 0. Alright? Let me remind you guys again about your unit circle. This is the point 1, 0. Okay, so again, that's cosine and sine. Alright, so sine 0 is 0, cosine 0 is 1. Negative sine is 0, 0, cosine of 0 is 1, so that's negative 1. Sine of 0, 0, cosine is 1. Okay, and now we're going to write this out. Let's see. Okay, so it's the first term, 0, and then it's 1 over 1 factorial x. Now remember, we're not putting x minus c this time. It's just x. And then it's 0 x squared over 2 factorial. And then negative 1 x to the third over 3 factorial. And then 0 x to the fourth over 4 factorial. And then positive 1 x to the fifth over 5 factorial. Okay? And again, you're going to notice that this time all these terms cancel out. Just a little bit different. With cosine, we were left with the even exponents, and with sine, we're left with odd exponents. So I want to get you guys to like kind of see the patterns here. Okay? And let's go ahead and write, let's see here, our terms. It didn't really like leave me a lot of room, so I don't know exactly where I'm going to write this, but here, we'll just go up here. Okay, x minus x to the third over 3 plus x to the fifth over 5 factorial minus x to the 7 over 7 factorial plus. Okay? Now, we're going to go ahead and write a general term here, okay? We haven't done that for the other ones, but we're going to try to write a general term. Now, you guys notice if I put a 1 right here, okay? These are all just going to the odds. There are a couple of ways to generate odd numbers. Even numbers you generate with 2x, or I'm going to use n, sorry, 2n. Odd numbers, you either generate with 2n plus 1 or 2n minus 1, depending on like what works better for that problem. Okay, so for this, I'm going to use 2n minus 1, because then my first term is 1, my second term is 3, my third term is 5. You can test that. And then it matches these same numbers down here, right? 3 factorial, 5 factorial, 7 factorial. So I'm going to write it over 2n minus 1 factorial. Okay? Okay. And then, sorry, I was like about to say something, but I'm going to change it, what I'm going to say here. Now, okay, you guys, let's like match these up. This can be a little confusing. So look, in order to get 1 here, I had to start with n equals 1, because then that's x to the 1 over 1 factorial. Alright? Now this, even though it has 3's in it, it becomes my second term. Okay? And so that's x to the third over 3 factorial. And even though it has 5's in it, it's my third term. So if I put in 3, it's x to the 6 minus 1, it's x to the 5 over 5 factorial. Okay? So that's what those terms are. So now, when I want to alternate, we have to do, whenever you want to alternate something, okay, you either go like negative 1 to the n, or negative 1 to the n plus 1, or negative 1 to the n minus 1. Okay, depending on whether it starts with a positive or negative. So this one starts with a positive. So I actually am going to do, it doesn't really matter between those two. You can pick whatever you want. But let's say I'm going to do -1 to the n minus 1. Because now on the first term, it's -1 to the 0, which is positive. Second term is -1 to the 1, which is negative. Third term is -1 to the 2, which is positive, like that. Okay? Now look, to be honest with you, the general terms can be very, very tricky to write. This is what I mean by the general term. And they're, like, you can usually, like, try to figure them out, but they can be a little bit tricky, okay? All right. Find a power series for f of x centered at 1 if f of 1 is 2 and f of n1 is n factorial. All right, so now we have this kind of a problem here where we're going to go like this. All right. Let's kind of list these out real quick. F of 1 is 2. Now f prime of 1 means it's n factorial, and that's n. So that means it's 1 factorial, which is 1. F double prime of 1 is 2 factorial, which is 2. F triple prime of 1 is 3 factorial, which is 6. And so on. Okay? So when I write my power series, alright, it always just starts with this first term, okay? 2. And then it goes to, now you can use the factorials if you want, or you can use like the actual numbers. It doesn't really matter. But it's a little easier to see what happens if you use the factorials, okay? So then my next one is 1 factorial over 1 factorial. Now look, centered at 1, which means I have to put x minus 1. And then my next one, my derivative is 2 factorial over 2 factorial, and then it's x minus 1 squared. And then it's 3 factorial. Now look, that I'm getting from there over 3 factorial. That's just part of my problem that I always use, x minus 1 to the third. And what you're going to notice, at least on this one, is that the 1 factorials, 2 factorials, 3 factorials, they all cancel out. Okay? Alright, so my power series is going to be 2x minus 1, x minus 1 squared, x minus 1 to the third, like that. Okay? And then, does it want us to do anything with that? No, not really. We're just kind of like good to put it like that. Now, here's the thing that's kind of weird. This part, you know, we can write as like a summation, but this doesn't really follow that pattern. And so what you end up doing is you just go like, it's 2, and then that to the n starting at 1 to infinity, you know? And so you could write it like that because the 2 didn't like necessarily follow the pattern of it, if that makes sense. Okay? So let's see what we're going to do with this assignment. You really have to pay close attention when it says show all derivatives. Okay? All of these say show all derivatives. Alright? Show all derivatives. Okay, so most of these say these. Yeah, this is crazy. Alright, so let me do an example with you. Maybe we'll do number 4 because number 4 is a bit tricky. Alright, so let's do this one together. Use the formula to find a fifth degree Maclaurin. Now remember, Maclaurin means centered at 0, so that's helpful. That's not like too bad. But we have to do our fifth degree. We got to start with f of 0. Actually, before I even do that, I'm going to write all my derivatives. If it's a fifth degree, now once you go up here, you just start going like f, and then you put it in parentheses so it doesn't look like to the fourth, to the fifth. Those are all my derivatives. Alright? And you might be thinking, well, this is going to absolutely suck. It's x times e to the x. That's a bunch of product rules. And you're actually kind of right. Okay. So my first one is just x e to the x. Now, if I do a product rule on my second one, it's derivative of the first, 1 times the second, plus first derivative of the second. Okay? I'm trying to decide if I want to factor this out, make it a little easier or not. No, I don't think I will. Okay, now, this, we just take a regular derivative of, right? That's e to the x. This, we got to do another product rule. Derivative of the first times the second, first times derivative of the second. So, if you notice, this becomes 2 e to the x plus x e to the x. Okay? Now, that one, I just do a regular derivative. That one, I do a product rule. And it goes derivative of the first times the second plus first derivative of the second, which turns into 2 plus 1. So it turns into 3 e to the x plus x e to the x. Do you guys feel comfortable at this point stating what this pattern is going to be? Let me box them and I think you'll see it. So x e to the x, 1 e to the x plus x e to the x, 2 e to the x plus x e to the x, 3 e to the x e to the x. So I think this is going to be 4 e to the x plus x e to the x, and 5 e to the x plus x e to the x. Or x to the e, that was so silly. Okay. Alright, and so here are all my derivatives. Okay, now I am plugging in x equals 0 for each of them. Alright? And we're going to find f of 0, f prime of 0, f double prime of 0, f triple prime of 0, f quadruple prime of 0, and f whatever of 0. Quintuple of 0. Okay? Now think about this, guys. When I plug in 0 to these, well, that's just going to be 0. Now, that part, whoops, not that part. That part is 0, and that part's 1 e to the 0. And e to the 0, anything 0 is 1, so that part is just 1. So it's like 1 plus 0. And then that goes to 0, and 2e to the 0 is 2. And then that goes to 0, and 3e to the 0 is 3. Okay? That goes to 0, 4e to the 0 is 4, and that goes to 0, and 5e to the 0 is 5. And then here's how you write your polynomial, okay? So I'm going to write it first with just everything so you can see it, and then we'll go from there. This is centered at 0. So this is going to be 1 over 1 factorial x, 2 over 2 factorial x squared, 3 over 3 factorial x third, 4 over 4 factorial x 4, and 5 over 5 factorial x 5. Okay? Now think about how we could simplify this down. This is 2 times 1, this is 3 times 2 times 1, this is 4, 3, 2, 1. This is 5, 4, 3, 2, 1. Well, what's going to happen is, and I won't put my 0, I guess. Okay? What's going to happen is, that 2 cancels with that 2. Now I still have 1 on the bottom, which, this is what my pattern's going to be. That's going to be 1 factorial. And then that 3 cancels with that 3, but I still have 2 factorial. And then that 4 cancels with that 4, but I still have 3 factorial. And so on, okay? That 5 cancels with that 5, but I still have 4 factorial. Alright? Formula, find the 5th degree for x e to the x. So, let me look if there's any other ones I want to talk about real quick. Okay, so this is what you're going to be doing for each of these problems, especially where it says show derivatives. And then some of them go like this, like number 2, use the problem from 1 to approximate that. So what are we going to do? We're going to let x equal a half, because that's what square root is e to the 1/2. Okay, we'll use that. for number 7, use the problem from 6 to approximate ln of 1.3. So we're going to let x equal 1.3. But it should be pretty close because, like, this is centered at 1 and we're doing 1.3. This is centered at 0 and we're doing 1/2, so we'll see how it is. Okay, do a few more where you're showing all your derivatives. Alright, I'm going to say to do 1 through 10 for this, for sure. And then we'll look at, like, some other questions in class, too. But 1 through 10 is good. Good start for that. Alright? Good luck, guys.